Hi, my name is Celeste Cunningham, and I'm doing my PhD at the University of Ottawa. Today, I'll be talking about my project on carbon deposition and preservation in ancient deep-sea levee sediments. The rocks I study belong to the Windell supergroup, which is a 6 to 9 kilometer thick succession of mostly marine rocks deposited on a passive margin after the breakup of Rodinia in the mid-to-late Proterozoic. My research group, led by Bill Arnott, studies the deep marine slope deposits of the Windell supergroup, and my doctorate project looks specifically at the levee deposits associated with slope channels. My fieldwork is conducted at the Castle Creek study site in BC, Canada, where levee deposits are exceptionally well exposed due to glacial polishing. This allows for detailed observations to be made at a wide range of scales. Additionally, samples taken from the field were examined using both optical petrography and scanning electron microscopy, as well as analyzed for TOC and carbon isotopes. 2 organic-rich facies have been recognized at this site: organic-rich sandstone and organic-rich mudstone. The TOC in these facies can be as high as 15% once they've been adjusted for the effects of green schist metamorphism, which is estimated to have resulted in the loss of 50 to 80% of the original content. Organic-rich mudstones are black and extremely fissile, and consist mostly of clay with lessile amounts of silt. They also contain abundant rhomboidal pyrite, as can be seen in the photo. Organic-rich sandstone beds consist of alternating bands of black, mud-rich sandstone and orange, highly cemented sandstone. Soft sediment deformation, such as flame and lode structures, are quite common in these bands. Organic-rich sandstone is the more common of the 2 facies and constitutes most of the organic-rich beds at Castle Creek. The OM can be grouped into 3 types: discrete silt to sand-sized carbon grains, sand-sized organomineralic aggregates, and nanometer to micrometer scale coatings around clay grains. Types 1 and 2 are interpreted to be detrital grains sourced from disaggregated bacterial mats that grew on the continental shelf before becoming remobilized downslope. However, these 2 types are relatively uncommon. Type 3 constitutes about 90% of the OM, and it houses thin, black coatings around and in between clay grains. The clay grains in the black, mud-rich sandstone bands, like the clay grains that comprise the OM-rich mudstones, are associated with this type. This OM is interpreted to have originated as freely suspended micro and nanoscale organic compounds and EPS from the upper water column over the continental shelf. These then became physically and/or chemically adsorbed onto the surface of clay grains and were subsequently resedimented downslope. So why is the OM concentrated in levees? Although primary productivity is highest on the shelf, OM can get transported downslope by sediment gravity flows. When this happens, much of it is adsorbed onto clay grains, as we've seen, and as such is concentrated higher up in the flow and ultimately ends up overspilling the channel and being deposited on the levees. The high sedimentation rates in this environment, coupled with the additional protection by chemical adsorption, prevent its destruction by oxidation or respiration, and this effectively sequesters huge amounts of carbon in the sediment and acts as a sink for atmospheric CO2. Significantly, this preservation can occur without any special conditions, such as bottom water anoxic events in the ocean. This study has shown that considerable amounts of carbon can be buried in deep-sea levee systems. However, carbon burial in the Neoproterozoic is not necessarily representative of modern systems. In the Neoproterozoic, terrestrial plants had not yet evolved, and so the OM being transported downslope was only marine and as such was dominated by these organic compounds bound to clay grains. However, recent studies of modern systems have found that terrestrial OM constitutes a significant portion of the OM found in levees and in other deep-sea sediments, and that most of this OM actually occurs as grains in sands rather than in muds. This suggests that although carbon burial in levees was significant in the Neoproterozoic, it is even more so now. For example, recent studies have estimated that approximately 3.5 million tons of new organic carbon are delivered annually to the Bendel fan system. Future studies should focus on examining the relative input of terrestrial and marine OM and the mechanisms and efficiency with which each isle presided throughout geologic history in order to better evaluate past and present global carbon fluxes. Thank you for your time.